Hey guys, in this session we are going to be covering the NCEA Level 3 Calculus Algebra Complex Numbers paper from 2019. So the way this video works, or the best way you can actually watch this video, is pause the video at the start of each question, try the question out by yourself, and then have a look at how I go about answering the questions. Now, just because I answer it in a way that you might actually find another way that you answer this question, and that's absolutely fine as long as you've got the correct working out. That's the most important thing. And I'll also be talking about what you need for achieve merit and excellence in these questions. Okay, so without further ado, let's get started. So let's get into it. Question 1a. What we've got here is we've got a quadratic equation, and we've been asked to solve in the form of a plus square root bi. So with this question, the best way to do this is by using the quadratic formula. So what we have is x is equal to minus b plus or minus b squared minus 4ac over 2a. And we're going to make sure we put in all our a value, b value, and c value. So a in this case is 1, b equals minus 4, and c is equal to positive 7. So with that in mind, we're going to start substituting these values in. So we've got negative of negative 4 plus or minus b squared is negative 4 squared minus 4 times 1 times 7. And all of that is now divided by 2 times 1. So x is equal to 4 plus or minus square root of 16 minus 28 over 3. Sorry, over 2. Silly mistake. And then we can say that x is equal to 4 plus or minus square root of negative 12 over 2. And from here, what we can do is we can rewrite negative 12 as positive 12 times I squared. But I'll just do that one extra step that as negative 1 there. So just a reminder that I squared is equal to negative 1. So then we can rewrite this as x is equal to 4 plus or minus square root of 12i squared over 2. But the problem is we want this in a plus square root of bi format. So what we can do is we can break that 12 further down and write it as x equals to 4 plus or minus square root of 4 times 3 times i squared. And that whole thing is divided by 2. So then x is equal to 4 plus or minus, now square root of 4 is 2. Square root of 3, I can't really do anything with it. Square root of I squared is going to be I, so that means that square root of 3 is still inside the bracket. And all of this is divided by 2. And of course, the 2's are getting cancelled. Well, before cancelling it out, I might just do one more step. So just to show you what's happening. So we can rewrite this as 4 over 2 plus 2 over 2 root 3 multiplied by I. Now notice that I is actually outside that root 3 symbol. So then we can rewrite this as 2, and this is just 1. So our final answer is x is equal to 2 plus root 3i. So we can say that a is equal to 2 and b is equal to 3, because that's what we've been asked to find out. So grades wise, this is an achieved question. A bit of a long question for achieved, but you know, it works out real nicely. Cool. So let's go to question 1b. All right, so with question 1b, what we have is we've got a polynomial that's divided by x minus 3. The remainder is 38. So all that means is we could actually say that f of 3 equals to 38. Because if the remainder is 0, remember that f of 3 would equal to 0 if remainder is 0. And because in this case the remainder is actually 38, we can say that f of 3 equals to 38. So all that means, now if you're wondering how I got 3 in there, basically the first step I should have done is x minus 3 equals to 0, x equals to 3. Let's get rid of that. And because x equals to 3, that is where the 3 is actually coming from. So now I just need to substitute 3 wherever x is. So 2 3 cubed minus 3 squared minus 4 times 3 plus p, and all of this is equal to 38. So I've got 2 times 27 minus 9 minus 12 plus p equals 38. So combining all together, 54 take away 21 plus p equals 38. This is 33 plus p equals 38. And we can see that p is equal to 38. Take away 33. So p is equal to 5. That's all for this question, which also gets you a grade of achieved. Okay, so moving on to question C. So with question C, what we have is two complex numbers, q plus 2i, v is equal to 1 minus 2i. Now we've been given that the modulus of u divided by v is 13. Find all the possible values of q. So our first step is to actually figure out what u over v is. So to do that, what we have is we've got q plus 2i divided by 1 minus 2i. Now remember that, if you want to find modulus, you want to have the denominator to be rationalized. Now, of course, you might actually find a completely different way. That's absolutely fine as well. So what I'm going to end up doing here is I'm going to multiply it by 1 plus 2i and 1 plus 2i. So when I actually do this, I'm going to get q plus 2i, q plus 2i, and then plus 4i squared. Then in the denominator, I will be getting 1 minus 4i squared. So now for the numerator, I need to have all my real values together and all my imaginary values together here. So that's what I'm going to do. And that's all divided by 1 minus 4 times I squared is negative 1. So I forgot this I squared as well here. There's an I squared there, so that's going to be negative 1. So what I've got is q minus 4 plus, I'm going to put I in a bracket, and I'm going to get 2 plus 2q. All of that is divided by 5. So now I can take the real part squared and the imaginary part squared. So the real part is q minus 4 over 5, and the imaginary part is 2 plus 2q over 5. So the real part squared plus the imaginary part squared equals, and remember the square root of that is equal to 13, because that's what the modulus is. Why do I have a feeling that I'm going to do this a really long way when there's probably an easier way to do this? It's fine, let's just keep going. Let's see what happens if we do this method anyway. So I'm going to get q squared minus 8q plus 16 over 25 plus 2 times 2 is 4 plus 4q and 4q squared over 25, and of course the square root of all of this is still equal to 13. So I'm going to simplify whatever's in the square root, sorry, inside the square root. So basically I've got q squared plus 4q squared is equal to 5q squared. Then I've got minus 8q, 4q, and 4q will become 0. Then I've got 16 and 4, which makes it 20. And that's all equal to 13 so far. Now, what I could do is I could actually simplify that whatever's inside the square root further by taking 5 as a common factor. I'm going to get q squared plus 4 over 25 equals to 13. And of course 5 and 25 cancel each other to give me q squared plus 4 over 5 equals to 13. Now I could get rid of the square root symbol by squaring both sides. And I'm going to get q squared plus 4 over 5 is equal to 13 squared, which means q squared plus 4 equals 13 squared is 169 times 5. So q squared plus 4 is equal to 845, and then q squared is equal to 845 take away 4, which is 841. And then I can say that q is equal to plus or minus 29, which is the square root of 841. So as I said to you guys, I think I did this in a very long-winded way. There is another way of doing this, and I think if you have a look at the answer schedule, they've actually done it a slightly shorter way as well, which, you know, does make sense. I think in the answers they've pretty much gone, this is their step 1 right here. So they've missed all of those parts, those extra parts. Yeah, so with achieved, so third line, 1, 2, 3. They're looking at somewhere here for achieved, and then for merit is getting that final answer. Alright guys, let's go to the next question. Cool. So with this question, question D, this is a very common question that keeps appearing again and again every year. So we have Z is 1 minus 2i, and it says if C is real, find the value of C in the other two solutions. So because 1 minus 2i is a solution, what you can do is you can actually substitute 1 minus 2i into that equation. So what I mean by it is, because Z of 1 minus 2i is a solution, if it's a solution, then we can say that 2 times 1 minus 2i to the power of 3 minus 5 times 1 minus 2i squared plus c times 1 minus 2i minus 5 equals to 0. Now guys, at this point, I know like you have a calculator, so take it out and actually work out 1 minus 2i cubed there. So what I'm going to do is, you can do it the long method if you want to. There's like, again, this question has like a multiple ways of doing this, but I'm just going to use this because I can. 2i to the power of, oh, that's going to be minus 2i to the power of 3. So if you want to figure out where I is, remember that that's I is right there. So this is now equal to negative 22 plus 4i. Then I've got to do the minus 5, so minus 5 multiplied by 1 minus 2i squared. Now that's equal to 15 plus 20i. And the c times 1 minus 2i, I'm going to leave it as it is. Minus 5 equals to 0. So now combining everything here, what I'm going to get is negative 22 minus 15 minus 5. That gives me, what is it, 27, negative 12 plus 24i plus c times 1 minus 2i equals to 0. And then I can say that c times 1 minus 2i equals positive 12 plus 24i. No, minus 24i. And then c is equal to 12 minus 24i divided by 1 minus 2i. And then c is equal to 12 times 1 minus 2i divided by 1 minus 2i therefore C is equal to 12. So I've done the first part of this question where I've figured out what C is. Now remember, with the solutions, right, if 1 minus 2i is a solution, then we could also say Z is equal to 1 plus 2i is also a solution. So now what we're going to prove is, or what we're going to try and figure out is, what is the third solution, right? Now, having a look at this, and I think this is kind of like where you understand how do I say it, how complex numbers work, or even just like cubics, how do they work. So because our first solution, and I'll kind of take a bit of time on this, okay, so don't worry about it. So our first solution is 1 minus 2i, which means in the brackets it's going to look like this, Z minus 1 minus 2i, because that's our first solution. Now our second solution is 1 plus 2i, which is going to look like this. Okay, because remember the question, like when x equals to 3, then x minus 3 is the factor, and like that. So that's exactly what's happening here. Now, because this is a cubic, we're going to have a third bracket. And in this third bracket, we're going to have something like this. It could be AZ plus B, for example. Okay, when it's asking for the last solution, we've got to figure out what this bracket is and then put it equal to 0 to figure out what the last solution is. Now, there's a couple of things to understand. We can figure out what A is, because look at this. Z multiplied by Z multiplied by AZ should equal to 2Z cubed. So we can actually write that here. Z times AZ should equal to 2Z cubed. Therefore, we can say that A is equal to 2. Okay? Now, the next step is to try and figure out what that B value is. To do that, we can say B multiplied by this should equal to minus 5. So that's what we're going to do here. So we've got negative times negative 1 minus 2i multiplied by negative of 1 plus 2i multiplied by B should equal to minus 5. So having a look at this, our two negatives cancel out each other, and what we have is 1 minus 2i times 1 plus 2i times B equals minus 5. So if that's the case, we can actually expand this bracket here. 1 minus 2i times 1 plus 2i would be 1 minus 4i squared times B equals minus 5. And I'm going to get 1 minus 4 times negative 1 times B equals minus 5. And what I have is 5b equals minus 5, and b is equal to negative 1. So to get my third solution, I have to put ax plus b equals to 0. And because it's 2x minus 1 equals to 0, 2x equals 1 and x equals to a half. So we found C, and we found our three solutions: 1 minus 2i, 1 plus 2i, and a half. So the way the grades work in this case is, if you get all two of them, two solutions found and C found gets you a merit. The other two solutions, so you need both this one and the C value to get a merit. But if you get just one of them, so you either get this C value or you get these two, then you actually get achieved. Cool, that's it for this question, guys. So it's a bit of a long question, but the reality is that it's been one of these questions that's just come in every year for the last, I don't know, 7 years, 6 years that I've seen it. Anyway, let's get to this excellence question here. So what we've got here is we've got x and y are real. and we've got to figure out what they are. Okay, so what we need to do is... Alright guys, so for this question here, there is multiple ways of actually doing this, and I'm going to try and do a completely different method than what they've shown in the answer schedule. So I'm going to write this as 1 plus x plus iy equals 1 minus 2i and plus 1 over 1 plus I. Because what I'm going to try and do is I'm going to combine the right hand side as a fraction, and then I'm going to flip it upside down just to see whether it'll work or not. So at this point, what I'm going to do is I'm going to have them with same denominators, which means I would need to multiply this 1 minus 2i by 1 plus I in the numerator, and in the denominator by 1 plus I. So when I do this, I'm going to get 1 over x plus iy equals to, now I need to expand that brackets, so I've got 1 minus 2i times 1 plus I plus 1, and the whole thing is now divided by 1 plus I, because that's all in that one common denominator. So looking at that numerator of that on the right hand side, I've got 1 times 1, which is 1, 1 plus I minus 2i minus 2i squared plus 1 over 1 plus I. Kind of carrying on here, 1 over x plus iy equals 2 minus I minus 2 times negative 1 over 1 plus I. So once again, carrying on, negative 2 times negative 1 is positive 2, so I've got 4 minus I over 1 plus I equals 1 over x plus iy. So at this point, I can flip the fractions. So when I flip the fractions, I'm going to get x plus iy equals 1 plus I over 4 minus I. So at this point, I've got to rationalize the denominator. So I'm going to multiply it by 4 plus I and 4 plus I. So x plus iy, and in the numerator I've got 1 times 4, which is 4, 1 times I, which is I, then I've got 4i plus I squared, and in the denominator I've got 4 squared minus I squared, so I've got x plus iy equals 4 plus 5i minus 1, because I squared is minus 1, and then 4 squared minus negative 1. Now 4 squared is 16, so let's actually write that. And what I've got is x plus iy equals 3 plus 5i over 17. And I can split that up to 3 over 17 plus 5 over 17i. And I can see that x is equal to 3 over 17 and y is equal to 5 over 17. So this is the correct answer, which gets you an excellence. But in terms of merit, equates real and imaginary parts, correct reduction of expression to 2 terms. Correct reduction to 2 terms. Where would I put that as a merit? Yeah, because I did this in a slightly different way, rationalize as a term gets you an achieved, so that could mean that you could, because this is rationalization, you could get an achieved for that, but then you could have done rationalization earlier as well. Reduction or equates real and imaginary parts. Reduction of 2 terms. Yeah, I'm not sure what that actually means in that answer schedule, but like I said, the answer schedule has a slightly different way of doing this question, and I've done it in a different way. So yeah, I'm gonna kind of leave it at that, guys. Okay, so that's the end of question 1, and now we go to question 2. So with question 2a, what we have is a nice bit of substitution. P dash is going to be 3 plus I. So therefore, when we have P dash minus 3Q, we're going to get 3 plus I minus 3 times negative 2 plus 5I. Now be very careful with this putting a bracket here, because so many times kids don't put the bracket, and then that means they forget about that negative 3 times positive 5I as minus 15I. That they always do this. Somebody will always make this mistake. So 3 plus I minus 3 times minus 2 is minus 6. And I mean, this is what I'm talking about. Sorry, minus 3 times minus 2 is plus 6. And minus 3 times positive 5I is negative 15I. And this is where the kids make the most mistake. They forget to put the bracket, and then they end up with some like positive 15I and do silly things. Cool. So what we have for our final answer is 9 minus 14I for a lovely achieved grade. Let's go to the next one. Next question, what we have is a nice rationalizing question. So all we have is 3 over 4 minus root 5. So we're going to multiply it with 4 plus root 5, and in the numerator by 4 plus root 5. When we do this, we're going to get in the numerator 12 plus 3 root 5, and in the denominator we're going to get 4 squared minus 5. Remember, it's 5 because square root of 5 times square root of 5 is just 5, and we don't need to worry about the inside terms. So we're going to get 12 plus 3 root 5 divided by 16 minus 5. So we're going to get 12 plus 3 root 5 over 11, which of course we can rewrite this as 12 over 11 plus 3/11 of root 5. So we can say that A equals 12 over 11 and B is equal to 3 over 11. So this is another achieved grade. Cool. Let's go to question C. Now, question C, guys, I mean, I do this in a completely different way to what you might have been taught. And my method, it still works. Feel free to check out the complex roots video in the Mathdemic Level 3 series, or just come and have a look at it in the website. The link for the website is actually in the description below. All right, so how this works is that our first step is this. Z4 is equal to minus 16 p squared I. We are going to actually plot this complex number. So because it's negative 16 p squared I, it is going to be somewhere here, where that distance is negative 16 p squared. So that's the length of the complex number, the modulus. So we can see that Z4 is equal to 16 p squared. Remember that the length is actually a positive length, and we also need the angle. So we could actually have the angle going back like this, and if we're going back, we're going to write it as minus 90 degrees. So then Z4 is equal to 16 p squared cis 90, which means we use De Moivre's theorem to figure out what the first root is. So Z is equal to 16 p squared cis 90 to the power of a quarter. So with that in mind, we're going to get our first root, which is 16 p squared to the power of quarter cis 90 divided by 4. Yeah, so once that's the case, sorry, that should have been minus 90. That's my mistake. Minus 90 over 4. So then we can say that Z1 is equal to 16 to the power of quarter is 2, and then p squared times, I'll just do that one extra step there so you guys can see what's happening. So I'm going to get 16 to the power of quarter, p to the power of 2 times quarter, cis negative 90 over 4 is negative 22.5 degrees. So Z1 is equal to 2 p to the power of half cis negative 22.5 degrees. Now this is where I talked to in the videos that I've showed before is this. If you have 4 roots, you are going to get 4 solutions of, well, 4 roots, because that power there is 4, and the difference between these roots are 90 degrees. And the way we know that is because there's 4 roots and they've got to be spread out evenly, 360 divided by 4 is 90 degrees. So that means all we have to do is when we get our first answer, we just keep adding 90 degrees to it. We have our first answer, which is negative 22.5. Our second answer is going to be plus 90, which is going to be 67.5, and then add another 90 to it, which is 157.5, and then adding another 90 to it, which gives us 247.5. And I'm just going to check the answers there. I just want to show you guys what if we do one more, right? Like let's say if we go to the 5th solution, we're going to get 2p to the power of half. Says 247.5 plus 90 is going to be 337.5. But here's the kicker. 337.5 and minus 22.5, they are the same answer. So you can see that the answers are actually repeating itself. So what I will say is this. I mean, like, you could leave the answer between negative 180 and positive 180, or you could actually leave your answer between 0 and 360. But as long as there's 4 solutions and there are 4 different solutions, you're good to go. So grades wise, 4 correct solutions gets you a merit. And I think if you get one of those roots, you get achieved for it. Cool. So let's go to the next question. So with this next question, what we have is we've got a complex number and we want to figure out what are the values of m that makes this purely a real number. So first thing we want to do is we want to rationalize the denominator. So we're going to get square root of 3 plus mi over 1 plus square root of 3i multiplied by 1 minus square root of 3i. And in the numerator, we're going to get 1 minus square root of 3i. Notice that the I is actually outside of the square root symbol, all right? So we got to expand the numerator. So square root of 3 times 1 is square root of 3 minus square root of 3 times square root of 3 is positive 3. So that's going to become 3i. Then we've got mi times 1, which is mi. Then we have minus m square root of 3i squared. And that whole thing is now divided by 1 minus 3i squared. So simplifying all of this now, we're going to get square root of 3 minus 3i plus mi. I squared is negative 1, so I'm going to get m square root of 3 times negative 1, and that whole thing is divided by 1 minus 3 negative 1. So in the numerator, I've got square root of 3 minus 3i plus mi plus m square root of 3 divided by 1 plus 3. And if I was to keep carrying on, I'm going to get square root of 3 plus m square root of 3 minus 3i plus mi over 4. Now, it says that find all the possible of m's so that z is a purely real number. If z is a purely real number, then it should have 0 as its imaginary number. So because of that, we can say something like this. As z is purely real, mi minus 3i is equal to 0. So we can say mi is equal to 3i, therefore m is equal to 3. And that's basically it for this question here. Gets you a merit grade to figure out what m equals to 3. And writing an equation without I squared can get you an achieved. So I would probably say somewhere here will get you an achieved. Okay, so let's go to the next question. Now question 2e here is just a long question, that's all it is. So anytime you get a question like this and you've got nothing given to you, you can do something like this. Put z equals x plus iy, because that's our starting point. Now the next point it says is the modulus of z equals to 1, which is right here. So if the modulus of z equals to 1, then we can say that square root of x squared plus y squared, because that's the real part and the imaginary part, equals to 1. So then we can rewrite it as x squared plus y squared is equal to 1, because 1 squared is just 1. So these are all the information that we have. Now the next step is we've got to prove that this is purely imaginary. So what we're going to do is we are simply going to substitute our x plus iy in this and just start manipulating it around. So because z is equal to x plus iy, I'm going to do that, divided by 1 minus x plus iy. Now once I do this, our next step is to rationalize the denominator. So to do that, what we're going to do is we're going to go 1 plus x plus iy. Can't really do anything in the numerator, but in the denominator we can rewrite this as 1 minus x minus iy. So that's all good to go. And so what we need to do is we need to rationalize the denominator. So that means we need to multiply by 1 minus x plus iy, and in the numerator 1 minus x plus iy. Now no matter how you look at this, the numerator, we've got this ugly thing that we need to expand. We just can't help it. All right, but the denominator, at least we can do something a little cheeky by putting a couple of brackets around that 1 minus x to make things a little bit easier. But the numerator, we've got this really long-winded expanding to do, whether we like it or not. And I'm just going to kind of go with this, guys. I'm going to do this a long method, all right? So that means literally doing this. 1 times 1, 1 times negative x, 1 times positive y, iy. So doing that first, I'm going to get 1 minus x plus iy. Next, I'm going to repeat the process with x. So x times 1 is x. X times minus x is minus x squared. X times iy is xiy. Then I've got to do it with the iy itself. Iy times 1 is iy minus xiy plus I squared y squared. Now that's all divided by 1 minus x squared. And I don't have to worry about the inside terms, minus I squared y squared. So we've got this ugly numerator here that we need to somehow simplify. So I'm going to start hunting for terms now, or at least trying to get rid of terms. So let's see. We've got a minus x and a positive x, which we can get rid of. Sweet. We've got a xiy here and a minus xiy. That can go away. What else could we do? Okay, so there we go. So we've got 1 plus 2 iys, because we've got an iy here and an iy here. Then we've got minus x squared plus I squared y squared, and that whole thing is over 1 minus x squared minus I squared. I squared is negative 1. Actually, I just realized that I squared is negative 1 as well, so let's change that to negative 1. Negative 1y squared. Now when we do this, we've got 1 plus 2ix minus x squared minus y squared, and that whole thing is over 1 minus x squared plus y squared. Now the good thing is in the denominator there's actually no I. That's what we wanted to do. Then what we can do is we can actually rewrite this as 1 plus 2iy, and we're going to take the minus 1 out. So this is going to become minus 1 x squared plus y squared over 1 minus x squared plus y squared. Now remember that modulus, that first thing that we did where they said that the modulus is equal to 1. So if we go back right to the top there, There we go. There's that little thing that we kind of did. That's a clue. That's usually a clue to say this is something you need to use later for this question. So that x squared plus y squared equals to 1, which means I can replace this x squared plus y squared as 1. And I'm going to end up with 1 plus 2iy minus 1 times 1 over 1 minus x squared plus y squared. 1 minus 1 is 0, so all I have is 2iy over 1 minus x squared. Oh, sorry, that x squared should be outside the squared. Copy error. Plus y squared. So I can rewrite this as 2y over 1 minus x squared plus y squared I. And as you can see, this is purely imaginary. And so we've actually just proved that this is purely imaginary. So this grade here is an excellence. Correct expansion without I squared gets you a merit. So that means correct expansion without I squared gets you a merit, which means somewhere here you could get a merit. Fourth line, 1, 2, 3, 4. I don't see what they mean by fourth line is. Yeah, it's weird when they say that real and imaginary grouped. Yeah, 1, 2, 3, 4. Yeah, not understanding the criteria for the achieved in this case, but definitely that's what you're getting for merit and excellence. But I think even if you're rationalizing it somewhere like here, if you rationalize it, you should be able to get an achieved here somewhere as well. So yeah, that's basically it for this question 2, guys. It's not how do I say it? It's not a long question. It's just well, it is kind of long if you think about it, but the reality is it's a proof question, which is quite nice. It does kind of work out real nice at the end. Okay, so let's go to question 3 now. Okay, so question 3, what we have is two complex numbers, and we want to write u divided by v in the form of r sus theta. Now, if you had just forgotten how this looks like, u divided by v, so we've got, that means we take the modulus and we divide it by each other, which means we're going to get q squared over q cubed, and we're going to put that as cis. And what we have to do is when we divide two complex numbers in polar form, we subtract the angles. So we're going to get 3 pi over 4 minus pi over 3. So u over v is equal to 1 over q cis 3 pi over 4 minus pi over 3. Get your calculator. 3/4 minus 1/3, 5 over 12. So put that as 5 over 12 pi. That's basically it for this question to get an achieved. Okay, so let's go to question 3b. So with 3b, what we have is two complex numbers equals to this. Find the values of an x and y. So all you're doing is expanding the quadratic on the right hand side. So we've got x plus iy multiplied by 2 plus I. So we're going to get 2x plus xi plus 2iy plus I squared y. So what we're going to get is 2x plus xi plus 2iy. I squared is minus 1, so this is going to become minus y. So this is all equal to 3 minus I. So remember that we've got real parts. So the real part is 2x minus y, and the imaginary part is x plus 2y. And that's equal to 3 minus 1i. So in other words, the real part, which is 2x minus y, equals to 3. And the imaginary part, x plus 2y, equals to minus 1. So we're going to set it up as two simultaneous equations. And it's just a matter of solving it simultaneously. Now you can actually use a calculator for this to solve it simultaneously, that's fine. I'm just gonna kind of being a bit you know what, let's just do it in the calculator. Why are we wasting time with these things? So what do we go? Menu, go into equation, go into simultaneous. Number of unknowns is 2. So we've got 2, -1, +3. And we've got 1, 2, -1. And when we do this, we're going to get x equals to 1 and y equals -1. You're not going to waste time in exam time, guys, for doing things like simultaneous equations, because if you know how to do it, then might as well just use the calculator and just kind of be done and dusted with it, so you're not wasting time. So this is a achieved question. Okay, so ideally in a calculus paper you do not want to be spending like more than 2 minutes on an achieved question, like, so that's why I kind of go, well, if you can use a calculator, just do it and you're done and dusted. Cool, so let's go to question C. So question C, we've been asked to write x in terms of w. So our first step is to rearrange, get rid of this square root is what we're trying to do. So we're going to move w square root of x to the other side. And once we are there, then it is just a matter of squaring both sides. So we're going to square this and we're going to square this. So first off, 2 squared is 4. Square root of x minus 3 squared just becomes x minus 3 equals w squared is, well, w squared. Square root of x squared is just x. So expand this bracket on the right hand side. We're going to get 4x minus 12 equals w squared x. Now we want to write x in terms of w. So what I'm going to do is I'm going to bring all the x's together. So I could actually say something like this: 4x minus w squared x. Switch the 12 over to the other side, it becomes positive. And at this point, x is a common factor. 4 minus w squared equals to 12. And then x is equal to 12 divided by 4 minus w squared. I would actually say this is actually a pretty nice merit question. Kind of works out well. Correct equation with terms in x gathered in line 4. 1, 2, 3, 4. So this part here gets you an achieved for this question, and the final answer gets you a merit. Okay, so let's go to question D. So question D, what we have is 2 complex numbers, yeah, blah, 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 and given that argument u over v equals pi over 4. Now, one thing I'm going to say to you guys is this: in complex numbers, the angles, particularly the angles, the arguments that they give you, if they give you an argument of pi over 4, pi over 4 is the same thing as saying 45 degrees. And remember, 45 degrees happens when you have a complex number. When you have a complex number where the real part equals the imaginary part. Because if they are equal to each other, then what you're working with is an isosceles triangle, and then that is equal to 45 degrees. So real equals imaginary whenever you see 45 degrees or pi over 4. Because that's how you're going to get an argument of 45 degrees. Because remember, 45 degrees is inside an isosceles triangle. 45, 45, 90. That's what I mean by, sorry. So anyway, all we've got to do is we've got to do u over v and prove that the real equals imaginary. So for u divided by v, we've got 1 plus pi divided by 5 plus 3i. So we're going to multiply it with its conjugate. So we got 5 minus 3i and 5 minus 3i. When we do this, we're going to get 5 minus 3i plus 5 pi minus 3p I squared, and the whole thing is divided by 5 squared minus 9i squared. So now in the numerator, what we have is 5 minus 3i plus 5pi. Now minus 3p and I squared is -1 divided by 5 squared is 25 minus 9 times -1. So in the numerator, our real parts are going to be 5 plus 3p, because negative 3, right at the end there, if you see negative 3p times negative 1 is plus 3p, minus 3i plus 5pi, and that whole thing is over 34. So from here, we can say something like this. As argument of u over v equals pi over 4, therefore real is equal to imaginary. So in other words, this is our real part here, and this is going to be our imaginary part, and so they're going to equal each other, because when we draw this, we don't need to worry about the denominator, we just need to worry about the numerator, right? So here we can say that 5 plus 3p equals negative 3 plus 5p. We don't need to worry about the i's because we're just looking at the coefficient of i's. So at this point we can rearrange it. So we are going to get 5 plus 3, 5p minus 3p. So we're going to get 8 is equal to 2p, and p is equal to 8 over 2, or p is equal to 4. So grades wise, p equals to 4 gets you a merit. For achieved, third line or recurrent real grouped. So you're probably looking at achieved is somewhere here when you have to separate the real and imaginary part. All right, so let's go to the last question. Alright guys, so for this question here, what we have is prove this a quadratic equation equals to this. We'll have two solutions for all values of k. So the first thing to recognize is we need to prove that the discriminant, which is b squared minus 4ac for this equation, will always be bigger than 0 for all values of k, because that's what we're trying to prove. So k could be anything, and this equation will always have two solutions. So our first step is to rearrange and figure out what b squared minus 4ac is first. So we got x squared plus 3kx plus k squared equals 7x plus 3k. Rearrange it, so we're going to get x squared plus 3kx plus 7x, no, minus 7x, sorry, plus k squared minus 3k equals to 0. So we need to combine our a, b, c values. So what we're going to do is we've got x squared plus 3k minus 7x plus k squared minus 3k equals to 0. So when we have our discriminant b squared minus 4ac, this a equals to 1, b equals to 3k minus 7, and c equals k squared minus 3k. So we're going to actually work out what b squared minus 4ac is first, and then prove that it'll always be bigger than 0. So b squared minus 4ac is 3k minus 7 squared minus 4 times 1 times c, which happens to be k squared minus 3k. So expand the brackets. We got 3k minus 7 times 3k minus 7 minus 4 times k squared minus 3k. So we're going to get 9k squared minus 21k minus 21k plus 49 minus 4k squared plus 12k, which then simplifies to 5k squared. We've got 42k, negative 42 plus 12, which is negative 30k plus 49. Cool. So at this point, this is what our discriminant value is. All right, so we've actually figured out what b squared minus 4ac is. We've figured out that this is what it is. What we need to prove is that 5k squared minus 30k plus 49 has to be always then bigger than 0. So no matter what value of k is. And I'm looking at the answer schedule, right? The answer schedule has a very interesting way of actually doing this. So in the answer schedule, what they've done is they've actually completed the square and then proved that therefore if you substitute any value of k in there, it's going to equal to 0. My thinking is slightly different, and I don't know if this is correct or wrong. Maybe someone could actually help me out in this. If a teacher is watching, yeah, could actually argue with me on this one. But my thinking is this. I'm just looking at this particular equation right now, which is 5k squared minus 30k plus 49. All right. And I want to prove that it is always bigger than 0. And because my thinking is because it's a quadratic, can we just use the discriminant formula again? And if the discriminant of this yellow function is actually a negative value, that means that there are no solutions, which means it's also above 0. And the reason it's above 0 is because this is a 5k squared, which is a positive parabola form. Anyway, I just want to try it out, and then I'll show you guys how the answer schedule did it as well. So here, if I actually went b squared minus 4ac, I'm going to get negative 30 squared minus 4 times 5 times 49. So I've got 900 minus 20 times 49, 900 minus 980, which is equal to negative 80. And because the discriminant is negative 80 of the yellow, I can guarantee that this is always going to be bigger than 0. That's my thinking right now. I don't know if that'll be accepted as a final answer, but you know, like as I said, if there's any teachers out there that watch this and can confirm with me, because I'm going to say discriminant of 5k squared minus 30k plus 49 is minus 80. Therefore, no solutions, which means it is above x-axis and always greater than 0. So that's my thinking. I'm going to put this in a red box. So if somebody wants to check that out, you can. But what the answer schedule did was this. They did it like this. So they went 5k squared minus 30k plus 49 is what they had. They completed the square by doing this. 5k squared minus 6k plus 49. So they did it. So k squared minus 6k, they completed the square by doing k minus 3 squared. And then, of course, we've got to subtract that plus 9. So they added a plus 9 to it to make it 49 like this. Now, if you're not sure how I got that square bracket, so just to have a look at it here, if I have k squared minus 6k, I can rewrite this as k minus 3 times k minus 3, which is k squared minus 6k plus 9. And if I wanted to complete the square, I need to make sure I put that minus 9 next to it. So then this could be written as k minus 3 squared minus 9. And so that's basically what I did here. But I should have put it as minus 9, not plus 9. Sorry. So at this point, I can expand it, and I'm going to get 5 times k minus 3 squared minus 45 plus 49, which would mean 5k minus 3 squared plus 4. And at this point, I can say that 5k minus 3 squared plus 4 is always greater than 0 for all values of k, because k minus 3 squared will always be positive. Because remember, anytime you take a number and you square it, it's always going to be positive, and then positive number times 5 is positive, and then that plus 4 is going to be positive. Therefore, it's always going to be greater than 0, and therefore 2 real solutions. Now, I know I might have rushed through this last question with a couple of ideas here thrown, but I still believe that the idea I put in this red box is fairly valid one to go check out. So yeah, I'd invite anybody to have a look at it and kind of see where I came from. So grades wise, that final explanation is necessary for excellence. Completing the square correctly up to line 7 is getting you a merit. Line 7, 1, 2, 3, 4, 5, 6, 7 up to this part here, which is, and then achieved is getting a right expression for b squared minus 4ac. Alright guys, so that's basically it for this paper. I remember having a look at this paper last year and I thought this was quite a nice paper compared to the last few complex numbers. Fairly straightforward one, apart from that last question which had a little bit of thinking. So yeah, as always, don't leave any questions empty. Attempt all questions if possible, and use the calculator when necessary, so you're not wasting too much time with questions as well. So with that guys, I just want to say good luck for your exams. That's basically it for this video. As always, don't forget to like this video, share this video, and subscribe to keep up with the latest content guys. There should be some playlists popping up. Check them out. Great revision material there. And as always, thank you for watching.